Welcome to another video explaining the universe using the particle model. Today's video is about precession, and in particular precession of the gyroscope. And it turns out that quite a while ago, end of last year I think it was, I promised 3 different videos, and I did 2 of them. One is talking about the gyroscope and anti-gravity, where I claim that it's not necessarily anti-gravity, but that the gyroscope works with gravity to do what it does. Then I talked a second video about how the gyroscope, which we normally see falling down, actually moving up. Yeah, it's a special case, but nonetheless, gravity causes the gyroscope to move up. Then I was going to do the one on precession of the gyroscope, and I got stuck. Didn't happen. Because as I started to go through it, I just couldn't quite get it, and it took me all this time to at least get one possible answer as to why the gyroscope precesses the way it does. So finally, this is the one on precession. This one's on gravity. The next one will be a second part to this one. It'll be on the precession of the Earth. Okay, and precession, what does Wikipedia say? Precession is a change in the orientation of the rotational axis of a rotating body. In an appropriate reference frame, it can be defined as a change in the first Euler angle, whereas the third Euler angle defines the rotation itself. Well, good luck with that, because I didn't even study it, and reference frames remind me of relativity, and frankly, I don't know what the Euler angle is. So you can look that up and study it if you want to, but good luck, because it's got lots of math. Well, here's a better description from Britannica. Precession, a phenomenon associated with the action of a gyroscope or a spinning top, and consisting of a comparatively slow rotation, emphasis on slow, of the axis of rotation of a spinning body about a line intersecting the spin axis. This smooth, slow circling of the spinning top is precession. The uneven wobbling is nutation. That's another thing that we could talk about in the future. Not planning that right now. That line of force that they talk about is the net force of gravity that is acting on the gyroscope. Okay, so here's the standard explanation, and here's a toy gyroscope, and it's tilted, and it's spinning counterclockwise, and the net result is that the axle or axis of this also spins counterclockwise. Spin it the other way, it precesses the other way. It's deterministic. Angular momentum, this is the key thing. They start with angular momentum, is a vector quantity. More precisely, a pseudo-vector. In fact, I think of all vectors in general are called pseudo-vectors because it's a mathematical expression, has magnitude and direction. But it's a pseudo-vector, which means whatever is moving that top around to precess, it's not the vector. And yet they start with angular momentum, and it represents the product of a body's rotational inertia, Inertia does have something to do with it. And rotational velocity. Yes, both of those things have to do with the fact that the top holds its position. And so they start with angular momentum, and they give you all these equations, and you can derive the force. What's interesting about angular momentum is its direction. If you pick a point on the edge of the gyroscope here and watch it go around, it has linear momentum and angular momentum if it's going around in a circle. So that momentum is sort of horizontal, at least it's level with the top of the gyroscope. But the direction of the vector is this way. Yeah, there's sort of like a right-hand rule here that says somehow if you have gravity this way and you've got motion that way, you got a vector this way. Why the inertia goes with the surface around, the angular momentum and inertia goes that way and the vector goes up this way? Strange. Not liking that answer at all. Well, here's a video. This is actually right out of Wikipedia. You click on this link and you go there and you can see there it is. It's spinning. Now that rotor is spinning very fast in a clockwise direction. You can't tell that here. And the precession is rotating much slower. Well, that's going relatively fast as far as precession goes, but nonetheless, that's what it looks like. Well, I looked at a video. Watch this one very carefully. It's interesting what the guy does to explain it, because he doesn't use angular momentum and do anything that. He's trying to use forces, which is an excellent way to go about it. And as he goes through it, it seems generally to hold to what he's saying. The only problem is the way he starts. He claims, and if you look at this thing that's on an angle, he understands that there's a force in, let me do it this way with my other hand, if I get it over there. There's a force on here kind of pushing this way. That's what this blue one is about. So, in a sense, there's justification for that force, because if it's at an angle like that, you got a gravitational force pushing this way on the tire. But not so much down here. Down here, the force is the same direction, pushing it the same direction, and yet he has it, the green arrow is pushing this way. Why does he say that? Well, because this moves this way and this moves that way, so there must be a force. So he's telling you the direction of something, but he isn't telling you what's causing it. Doesn't even say it's gravity or not. It just says that's the way it moves, but it's implied that it is that. So he starts with something that where many times we hear an explanation of what it does, but not what it is. Well, there's another one here that does exactly the same thing. It kind of has a different view. There's that force pushing this way at the top, and here's this force this way pushing at the bottom. Again, there is no explanation as to what those forces are, but you can see here what he describes here is that this velocity vector, this is the linear velocity vector, basically caused by this is speed, and this force is pushing on this velocity vector, causing the velocity vector to change slightly its angle that way. Just the opposite here, there's a velocity vector here. This force is causing that velocity vector to move this direction, and the combination of those velocity vectors changing is what causes it to precess and go around. Again, no explanation as to where these forces come. He just says, there it is. That's the answer. It needs more than that. Anyway, direction. I've sort of mentioned this. The rotor spins clockwise. The axle precesses clockwise. The rotor spins counterclockwise. The axle precesses counterclockwise. The rotor spins fast. The axle itself, the spinning of the axle is fast because it spins as fast as the rotor, but it precesses very slowly. It doesn't you've got gyroscopes here can be 10, 12,000 RPM, and you got something that's going around maybe 10 times a minute. By the way, I did talk about spinning. Here, this talks about spinning. A video I did recently, I claim the moon does not spin, it turns, and you can watch that video. So this is deterministic. It always happens the same way. There has to be a specific reason for this to happen the same way. Always, the axle turns the same direction as the spin of the rotor, always. There must be a force, and the only force around that seems is Newtonian gravity. That's related to the direction of spin that determines this action. So that's what we're going to look at. Well, I apologize. Yes, this is complicated. But if we go at it slowly, we can maybe understand what I'm trying to say. Well, here's a F1, which is the net force of gravity caused by the Earth. The Earth, this is where this net force comes from. And this F1 is smaller, and I did this part I did deliberately. This is smaller, this is weaker, this is stronger. This is stronger, this is weaker. So you have a weaker force up here and a stronger force down here. That's an imbalance, and that's the kind of thing you look for. There's an imbalance. If there's going to be a net force pushing it one direction or the other, there needs to be an unbalance, and that's a key. That's the first key point. So you can take this vertical force here and break it into two vectors. And the way you do that is you take a component of this that's in line. You make one of the components in line with the velocity. This is the velocity. It's going counterclockwise. This is going counterclockwise, and this, with this force pushing down, it has a component in line with, and it causing it to accelerate. You can actually move this component up here, and you can see that you go from here to here, then here to here is the same as this. Well, not only do you have this in line, then you'll also take one perpendicular to it. First in line, then perpendicular. That's as simple as that happens. And then this force, this is gravity, this is the force of gravity, radial force, which I put down here. Moved it down here. You do the same thing here. You got this vertical force. This component is in line with this speed. This is perpendicular to it, and I move that up here, and that force is this direction. It's in the downward direction. Do that for all four of them. You got this force moving here, and you got this force moving up here. Now, what I'm trying to do here is show that there are forces on the axle, and frankly, it's in all directions. And it's not only at these 4 points, but every point on this rotor would do that. So, but this is sufficient for an analysis. Now, if the rotor is if the axle is going to, if this is counterclockwise, then this axle is going to go counterclockwise, which means it's going to go this way and around and back. It's going to go this way. This should be the dominant force, this direction. I didn't show that very clearly there, but what we're going to do is we're going to skip to the next one down here. And so what you have, what I've done here is, whoops, I'm jumping the gun. There's one thing I didn't say up here I needed to say. Go back. We already stated that we got an imbalance. The top half has a weaker force, a gravity force. The bottom half has stronger. So that probably means these two forces here are dominant down here, where these are weaker. So we need to pay attention to these two relative to those two. But over here you have an acceleration. This is trying to accelerate this point, make it go faster. This one's trying to accelerate, make it go faster. But you get over here, the gravitational force of acceleration is pushing against the velocity, trying to slow it down. Same thing here. This vector is trying to slow this down. So you've got trying to accelerate on one side this way, trying to decelerate on this side, and you actually got like compression, like twist, kind of a torque. One of the things they use to explain it is torque, but not this torque. So this is a little tricky, and I even would apologize that maybe what I'm saying isn't precisely true. But I'm going to make the statement that on this side, gravity has a weaker effect on this point because acceleration is stronger. Acceleration is taking if you calculate the next position of this point, and you take into its velocity plus the acceleration of it, in contrast to the gravity, the velocity is going to have more effect. The gravity has less effect. The gravity has less effect here and less effect here, whereas over here, this is trying to be, the speed has little effect. It has the same velocity, but there's a force trying to push it back when you calculate the next position. This combination of the velocity and the force slowing it down has a weaker effect than the gravity. So I would say the gravity here has a stronger effect here and here. Weaker effect on this side, stronger effect on that side. Now, this is what so you got two imbalances now, and you need these two imbalances to get this to the point where you say it's weaker here, it's weaker here, it's stronger here. Therefore, this is the force that dominates. This is stronger than this, and this is stronger than that. So this is the force that dominates, so there should be a net force that way. A combination of these two has a net force this way. It's the difference between this one and this one that makes this, and it's the difference between this one and this one that makes that. So you actually have two forces. That's true in a particle model. There's always forces both directions. G1 particles come come to the gyroscope from all directions, and they are hitting and pushing this way and pushing that way, up and down and sideways. And even though we talk about net forces as if that were the only thing there, both of those forces are here. So this is a small force because it's the difference between these two, and this is the difference. But even smaller is the difference between this vector and this vector. This one's smaller than that, and so the net force in the direction, which is the correct direction, very small. I mean, we've broken these forces down once, down twice, down 3 times to finally get there. Okay, so this is all about gravity versus speed. The force of gravity is weak on the top half of the rotor and stronger at the bottom. That's the first imbalance. The speed is the same all around, except that gravity tries to speed it up on the left, slow it down on the right, and you got a horizontal imbalance. And as a result, although these arrows, I did this one deliberately, where this is stronger than that, and so the net force on the axle in the counterclockwise direction is the difference between this and this pushing it, and that's a very small force. Okay, well, just as a reminder, back late last year I did 2 videos. I'll post these so you can look at them. This video gets a lot of activity. I'm pleased with that. I'm surprised this one doesn't. To understand why a gyroscope actually could move up caused by the force of gravity moving down, I thought would be interesting. But my next one, part 2 of Precession, is going to be about the Earth and the Ice Ages and the North Star, all of which are part of the precession or not of the Earth. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when we'll talk more about the universe using the particle model. He said that's what the Earth and the North Star and the Ice Ages. And I should, by the way, as a final thing, is show you this video. This is a video made by David talking about our book. David and I have been working hard on the book, and this is the icon that represents our book, and it's coming out soon. So look for it, and we hope that when it comes out, you enjoy the book. Thank you.